Hey, welcome back. This is Trigonometry, section 6.1. We're going to take a look at the law of sines today. So up to this point, we have been working with right triangles. Today, we're going to start working with oblique triangles. And in particular, we want to solve, quote unquote, solve the triangle, which means basically find all of the sides and determine the value of all of the interior angles. Okay, so first off, what is an oblique triangle? And you may be able to guess it is a triangle which is not a right triangle. Okay, so I'll just say no right angle. Okay. There's two versions. Two versions. The first version is where you have three acute angles. So remember, acute means in between 0 and 90 degrees. I don't even think you could say it's equal to. I think it's strictly in between 0 and 90. I'd have to look that up. I don't know if it's weak or strict inequality on that definition. It's not a definition I use every day. I apologize. Maybe I should pause the video, right? Yeah, let me pause the video and look that up, and I can fix that. Yeah, I'm right. It's strictly in between, so it can't equal 0 degrees, and it can't equal 90 degrees. So the first version, 3 acute angles, and those triangles will look something like this. Okay, and usually we're going to label the corners of the triangle or vertices of the triangle. We're going to go counterclockwise ABC. Okay. All right. The other version then is where you have 2 acute, and again in between 0 and 90 degrees, and then 1 obtuse. And the obtuse angle is from 90 to 180. Okay. So those characters will look something like this, where one angle will be greater than 90 degrees. Hopefully that looks like it's exactly 90 degrees. Let me try 2. It's a lot harder than you think, all right? You just try it on your own. There, I think that is greater than 90 degrees. So this is our obtuse angle. Okay, so 1 obtuse, and then, okay, those are the 3 types. Okay, the law of sine is this, it's basically 3 things that are equal to each other. So maybe I should show you what the law of sines are. Section B, we're going to derive these formulas. Derivation. And the thingamajig is A all over sine, and maybe I should draw a triangle, right? So here's a generic obtuse triangle, A, angle B, angle C, and then the sides opposite will have the same letter. So the side opposite angle A will be little a, the side opposite angle B will be little b, the side opposite of angle C will be little c. Okay, so given this picture, we can say that A all over sine of big A is equal to B all over sine of big B. But you can also say either one of those, so A over sine of A or B over sine of B is equal to C all over sine of C. Okay, so usually this is the way they write the law of sines, but in practice you're only using 2 at a time, right? You're not going to be using sort of a triple equation or something, no. You'll pick the first one and the second one, or the first one and the third one, or the second and the third one, right? And then you'll be able to use that to solve for unknown bits and parts of the triangle that you're working with. Okay, so we want to derive this fact, and we'll do that by kind of working with a generic obtuse triangle. So let me draw that. Here's my generic obtuse triangle. Labeling A, B, C, if you wish. This is side A, this is side B. I think we need side C labeled. And I'm going to drop perpendicular bisector down from C that will hit line C at a right angle, and I'm going to call that line H. I guess it's the it's is it the, it's not the hypotenuse, I forget what they call it. Anyways, there's that. It's called H. We're calling it H. Okay. Then we could work with the right triangle definitions. Okay, so I'm going to say, what is the sine of angle A? Right. Angle A is right here, and I'm working with this right triangle, this red triangle here. So it's a definition of the size of a right triangle. Sine of A, in this case, will be opposite over, okay, hold on. Sorry, I thought somebody was in my office, but they're not. So anyways, I'm going to work with this red triangle, and sine of A is opposite over hypotenuse. So in this case, using the letters H over B, and also consider sine of B. And it's going to give me, basically will allow me to produce the law of sines, at least part of it. So sine of B then, using this, I guess, let's make this blue triangle here, where this angle sine of B, opposite over hypotenuse, so in this case it will be H over A. And then you could solve both of these equations for H, just multiplying both sides by B. So you get B sine of A, and then here H is A sine of B. You're going to equate those two things, so you could think of it as just substituting. So substituting this in for H, and you get A sine of B equals B sine of A. Okay. And then we just divide both sides by the sine part of both sides. So, here I need to divide by sine of B. If you do it on one side, you have to do it on the other. But I also want to divide by sine of A, so it's kind of like multiplying by 1 over sine of A. Right. And what happens then? So these are gone. On the left, I'll end up with A over sine of big A, angle A. On the right-hand side, these guys go, and I'll be left with B all over sine of big B. And lo and behold, that's the first part of our law of sines. Okay. We could, I believe you could like rotate the triangle and then drop another perpendicular bisector and kind of do the same game. And then you are able to produce the other part of this equation, the C over sine C part. We're going to just leave that alone. This is the idea, and hopefully you can stomach using this formula from now on. Okay. So we're going to use it to solve oblique triangles. So that's kind of our next section here, solving oblique triangles. And there's several variations. The first two variations are kind of easy, but then they get harder. Okay, so we'll continue on solving oblique triangles. It turns out in order to solve all oblique triangles, given 3 bits of information, you're going to have to also have the law of cosines. Okay, and we'll see the law of cosines in 6.2. Okay, but for now, just looking at SAA, which is side angle angle. So the kind of example that we have given to us, A equals 46 degrees, big C equals 63 degrees, and little c, sorry, I apparently have hiccups, little c is 56. Okay, so let's draw our triangle and kind of label it what we have. So A, B, C. This is 63 degrees, this is 46 degrees, and little c is 56. Okay, so you can see, looking at the triangle, it goes side, angle, angle. Okay, so going here, is that, am I saying counterclockwise when I mean clockwise? No, this is then clockwise. So, you start with side and then angle, angle. Okay, so no, it looks like it's angle, angle, side, but it's side, angle, angle. So, okay. what do I need to do? So the first thing you want to do is get the low-hanging fruit, so to speak. So you know the sum of the interior angles of a right triangle. In other words, if you take A plus B plus C, that will equal 180. Okay, so if you know two of the parts, if you know A and you know C, you could solve for B. B will just equal 180 minus A, which is 46, minus C, which is 63. Okay, so we automatically get B for almost no work whatsoever. Okay, from this point, you're just going to use the law of signs to solve out for any of the other unknowns. So basically, you pick two of the expressions, and then you'll be able to fill in three of the variables, and you just solve for the third variable. Okay, so let's take a look at that. So I'm going to use the C part to sort of fill in one of the fractions. So I'll have C, which is 56, all over sine of big C, which is 63. And I'm going to try to solve for little a, because I know the sine, I know what the angle is. Big A is 46, but I don't know what little a is. So I have an equation here. I can solve it because it only has one unknown. Okay, so pretty easy to solve. It's just multiply both sides by sine 46. Okay, so I end up flip-flopping the equation. I end up with A equals 56 sine of 46 all over sine of 63. And then you go to your calculator. Make sure you are in degrees. Okay, that's very important. The book will tell you how many decimal places, and of course, you know, the software will tell you. Little mates are usually to the 10th place. Okay, so this is part 2. The only thing that's left that's unknown at this point then is little b. Okay, so I can do the same process again. I could work with 56 over sine 63, and then solve for little b, because I know the angle big B is 71. Okay, so again, you just multiply both sides by sine 71. So B will be 56 sine of 71 all over sine of 63. And if you put that in your calculator, you're going to get 59.4. Okay. And that officially kind of concludes the problem. You've solved your first oblique triangle. Okay, so that's the first variation. The second variation, then they will give you an angle, a side, and then angle in order on the triangle. So example 2 is that case. You have angle is 50 degrees. Your second angle, 33.5 degrees, and then letter side little b, which they're giving us 76. So that's, you know, and normally you would have to kind of draw it first to see the scenario that you're in. They're not going to tell you this is an angle side angle problem, right? So you're going to, you know, label, this is 50, this is 33.5. Don't know big B, little b is 76. Okay, so you can see it's angle, then side, then angle. You can't think of it as angle, and then so it's a little weird like that. You'll figure it out, though. I have faith in you. Okay, so what do we need? Again, the low-hanging fruit is going to be angle B. So first, you could say, well, B must be equal to 180 minus the other two angles, 50 minus 33.5, and that'll be 96.5 degrees. Okay, then it turns out you can just use the sine laws here to get the other bits of information. So I'm kind of set with the B part, so I'm going to put little b, which is 76, all over sine of 96.5. So you're kind of looking, you have to start with the ones that you know. So for the law of sines, you need both the side and the angle opposites at that side, okay, for part of it. And then on the other side, you're going to put, you know, either A or the C. Let's do the A first. just going in alphabetical order. This will be all over sine of 50. Again, multiply both sides by sine 50, you get 76 sine 50 all over sine of 96.5. Okay. Then little a will end up equaling 58.6 as your distance to 1 decimal place. Make sure you're in degrees. Thirdly, then, we could pull the same business, but with side C we want. So we have 76 all over sine of 96.5, and we are needing to find little c. So that'll be all over sine of big C, which is 33.5. Okay. So multiply both sides by sine 33.5, you end up with 76 times sine of 33.5 all over sine of 96.5. Okay, simplifying that a bit, that'll be 42.2, I believe. Okay, so those are fairly straightforward. This next case, though, isn't, and it's because one of the unknowns is going to be the angle in your formula, your law of sines formula, and because of that, you're going to end up having to use an inverse sine to find your answer, and because of that, you'll actually have two possible answers. Okay. So they call this in the book the ambiguous case. It's SSA, side-side angle. And it's kind of ambiguous because it may result in two answers. Okay, so the sort of it may result in part A, two triangles, B, one oblique triangle, C, one right triangle. I'll just put the symbol for triangle there so I don't have to write it out. D, no triangle. Okay, it's a good day when it's either no triangle or just one triangle. The two triangle problems turn basically into two problems for the price of one, so you never like to see those. But let's go ahead and take a look at the examples, right? So maybe it'd be better just to start with the two triangle case, okay? And so you could kind of see that play out. So this is actually example 5, and then I'll circle back and do the other two types. And we have two solutions here. Okay, so they give us our information, 40 degrees, A is 54, B, little b is 62. If you do your triangle, you could see the type. So it's 40 degrees, 54, and 62. So side angle, side, or side angle, I guess, side angle. Right. So you have to use this method. You can't get, you can't use the 180 minus blah because you're dealing with only one interior angle given. Okay, so you're kind of forced to begin with the law of sines. Even if I didn't tell you, you would be, if I didn't tell you how to solve these, you would be forced to do it in this way. So you'll start with the two A parts because big angle big A and then little a, right? So it'd be 54 all over sine of 40. And then on the other side, you're kind of stuck with the solving for B, right? So it's going to be 62 all over sine of angle B. It's one equation, one unknown, but the problem is you're going to have to do the sine inverse. So watch. I'm going to move the sine to the left side and then multiply the 54 over sine 40, or really divide that to the other side. So you end up with 62 sine 40 after all is said and done, all over 54. My next step, then I have to take sine inverse on both sides. So if you take sine inverse of sine of b, you end up with b on the left. And then on the right, you'll have sine inverse of 62 sine 40 all over 54. Okay. All right. Well, you can put that into your calculator, and of course you'll get an angle, you'll get an answer. Remember that the range of sine inverse is from negative pi over 2 to pi over 2. So you're going to get an angle in there. If the angle was negative, you're done. Okay, that's not going to work. Sometimes if the thing you're putting in the sine inverse, its output could be, it might not have an output. And that's the case when you have no right triangle. So we'll see that in an example here in a second. Okay, so sometimes this won't even work and you're done. And that's a good day. But other times it will work, and actually you'll have two answers. So if you put this into your calculator, you're going to get approximating to the nearest degree, 48 degrees. The only problem is that there's another angle that might work, because we could also consider not just the 48 degrees, which is right here, but this guy. Okay, this other angle of a triangle, an oblique triangle. So that other angle is going to be, you could call it like B something else, B bar, I guess. We'll say, what is that? How do I get that? It's 180 minus 48, which is 132. Okay. So it turns out there's two possible answers here, and so we'll go over and kind of have to split the problem into two parts. Okay, one for B and one for B bar. So the one where B is equal to 48 degrees, you can automatically then get C by using our sort of 180 minus 48 minus 40, and that'll give us, what is C then? 92. And then B bar is 132, so C will equal 180 minus 132 minus 40, which is a very small angle, but it still works, right? So again, with the oblique triangles, you can have one obtuse and then two acute, or you can have three acute. So for our case here, we have A, B, and C. That's two acute, and then I guess it's one obtuse. And then for A, B bar, and I guess let's call it a C bar, put a little bar across the top called C bar. That's also the same type, right? That's two acute and one obtuse. So I guess you get the same case in both. Anyways, then you have to solve out for what's left over, C, little c. So step 3, I guess, if you want to consider these as steps, you don't have to number the steps. Take the 54 all over sine 40, and then set that equal to little c all over sine of 92, and then you could solve for c is 54 sine 92 all over sine of 40, and then we put that in our calculator, and it turns out to be 84.0. Then over here, do the same spiel. So step 3, we have 54 all over sine of 40 equals little c. Where's my, I don't know, little c, all over sine of 8. And again, solve for c, you end up with c equaling 54 sine of 8 all over sine of 40. Okay, so that will be approximately 11.7. Okay, so this is like the worst when you get those two solutions, because like I said, it turns into basically two problems for the price of one. Okay, you'll be able to differentiate this case from the other cases at this step right here. Well, it's actually this step kind of, if you have no solutions, it will be that step, because the sine inverse function won't work in your calculator. It will say undefined or something. Okay. if it's the one case solutions, when you go over here to step 2, that's going to fail, okay, because one of the C values won't pan out. It's like it won't be, 2 of the angles will be bigger than 180, okay. So we want to see those things play out so you know what's going on. So the first one we'll look at will be the one solution case, and then we'll look at the no solution. So going back now in the book to example 3, one solution case, they give us A is 43 degrees, little a is 81, and little b is 62. And if you want to draw your triangle, you can. Well, sure, let's go ahead and try it. So 43, this is A, B, C, and this is little a, little b. We have little a and little b, so we put those in. So little a is 81, little b is 62, and I don't know what little c is, right? So big C and little c are unknown. And little b is unknown. So again, you're kind of stuck. You can't do the 180 minus a minus b because you're missing 2 of the angles. So you can't play that game. You're forced to kind of use the law of sines right off the bat. So you're going to, the 81, the angle a and the little a, so you use that. And then on the other side, you could work with b, right? So you have 62 all over sine of b. Solve for sine of b, so you can do a little bit of algebra. Sine of b will be equal to 62 sine 43 all over 81. Okay. Then take sine inverse on both sides, so you'll get b equal to sine inverse of 62 sine 43 all over 81. And then that will equal 31 degrees, okay, if you put that in your calculator. But again, there's also this other potential solution in the second quadrant. So if you have 31 degrees, there's also this other one, which is 180 minus 31. So you say, okay, maybe or 180 minus 31, which is 149. Okay. Then you could kind of proceed like we did in the previous example, right? You think it's going to cut into 2 different triangles, but the truth is, when we work with this other, let's call this B bar, when we work with this other triangle, it's not going to work out. Okay, so let's see. For the first case, we want to know C, so we take 180 and subtract away B and subtract away A, and you'll get big C is 106. And then you'll come over here and try to find the other C, we call it C bar. That'll be 180 minus the 43 minus the 149, and there's the trouble. This thing is negative. It's negative whatever, negative 12. So it doesn't work. In other words, we only have one solution. Okay, so then you just go back to the C guy. You want to find little c. So again, we'll use A to figure that out. Multiply both sides by sine 106. So little c will be 81 sine 106 all over sine 43. And so little c will be 114.2. And then that's it. Okay, then you're done. All right, so that's not as bad, but usually you're hoping for no solutions, and that way you have so a little less work to do. It's still work, but okay. So example 4 is this case where you have no solutions, and in particular, let's look at this example. We have big A is 75 degrees, little a is 51, and little b is 71. So again, you're just not able to get the other 2 angles unless you use law of sines. So we'll start with 51 all over sine of 75. Oops, I butchered that number. On the other side, we'll have to use the b value, 71 all over sine of big B. If you need to draw the picture, draw the picture. And usually you're going to have to, just to figure out which version you're dealing with. So anyways, solving for sine B, you'll get sine B equals 71 sine 75 all over 51. Okay. And then, of course, you get B equals sine inverse of 71 sine 75 all over 51. And it's worth kind of investigating what this expression is before you put it into the calculator, into sine inverse, right? If you plug that part into your calculator, it turns out to be 1.34. So there's no way it's going to work, because anything that goes in the sine inverse has to be in between -1 and 1. Okay? But if you do put it in your calculator, it's going to say undefined or some variation of that anyways, so it's not going to work. So you're going to end up just saying no solutions. Okay, so this won't work, and just write no solutions. Okay. Okay, so that's the big and the small of that. Let's take a look at one application, which is kind of neat. It's determining the size of a telephone pole, the height of a telephone pole, where the telephone pole is leaning. Okay, so we have this telephone pole sticking out of the ground, but it's leaning over to the side. And we're able to kind of measure the lean using whatever methods somebody in the field would have. And we figure out it's leaning 8 degrees from the vertical. Okay, and then you can also do stuff like, figure out the length of the shadow. So maybe you figure out the length of the shadow here is 20 feet. And then you could use some sort of like a, I don't know, one of those little scope things that has a compass on it in order to figure out the angle from that position. Like maybe you're standing here. You could figure out this angle from where you're standing to the top of the telephone pole. So maybe you figured out that to be 68 degrees. Okay, so you're trying to figure out the length of the telephone pole, and what this really is basically working with an oblique triangle as opposed to a right triangle. Okay. So this will be angle A, B, and C. Little c then, so what are we given? We're given angle A is 68 degrees. We can figure out angle B because this right here, this line at the vertical makes a 90-degree angle with the base, and then the telephone pole is leaning 8 degrees away from the vertical. So angle B is just going to be 90 minus that 8-degree lean. Okay, so that's going to give you 82 degrees for angle B. Automatically then you could find angle C, right? So that's the low-hanging fruit. I don't know if we need it, but you can find it, right? So it's 180 minus 68 minus 82, and that'll equal 30 degrees. Okay. So we know this angle up here. What are we looking for? We're looking for this distance, again, the distance of the telephone pole, this red line here, which traditionally we would think of as length A, little a. Okay, so it looks like we could probably use the law of sines to do that, right? So you'll say 20 all over sine of angle C, which is 30 degrees, equals that telephone pole length, which is A in this picture, all over the sine of 68. Okay. And then we should be able to solve that for A. Just multiply both sides by sine 68, so we'll get 20 sine 68 all over sine 30, which is equal to 37 feet. So it turns out the telephone pole is 37 feet tall. Okay. So interesting application. Anyways, that'll about do it. In the next section then we need to look at 2 more variations, and I know I forgot the video quiz again, as usual. They'll make the video quiz example. Let's make it this example here. So this one's the video quiz. Sorry about that. I think it's example 2 in the book. Okay, so video quiz is example 2. You may have to go back in the video if you weren't taking notes. Please take notes, just like you were in normal pre-pandemic class. You should be taking notes, okay? Okay, so example 2 is your video quiz. And okay, thanks for watching as usual, and we will see you next time.